Okay, so we're talking about the saponification of soap, no? And the question would be, in the reaction of triglyceride to produce our soap, the question is, how would soap have a cleansing action? How would soap have a cleansing action? Okay, so the cleansing action of the soap would be derived from its structure. Okay, so in the structure of the soap, there is what we call as the polar portion of the soap, and then you have the non-polar portion of the soap. So what is the polar portion of the soap? The polar portion of the soap comes from the carboxylate, and you have the C double bond O, name. Okay, this is again the shortcut of COO minus the carboxylate. But again, no, that oxygen is not bonded to oxygen. Oxygen is bonded to carbon. So you have your carbon double bond O and carbon bonded to oxygen. Again, this is a shorthand notation of the carboxylate. Okay, or even when you're talking about the carboxylic acid. Always know, again, I would like to emphasize, no, bantay makakita po mag-write the structure, oxygen is bonded to oxygen. Okay, they are not bonded to each other. Oxygen is bonded to carbon here. And there's a negative charge again on your oxygen. So here, if you remember your basic chemistry, you have your oxygen being an electronegative atom, it bears a negative charge. Okay, so the electron density is much higher on this part here. And this becomes our polar portion. And this being polar, you have an atom that is negatively charged. It can be easily have intermolecular force of interaction with water. And this part here, the chains, the hydrocarbon chains here are the non-polar portion. You don't see an atom that is an electronegative atom that bear a partial negative or a partial positive charge that's seen here. This is your non-polar option. This non-polar portion, and this is the portion that would be bounded to the dirt, to the dirt. Usually your dirt would have the oily part or the hydrophobic part. So this end becomes your tail, and this one becomes your head. And the head is your polar end, and this tail is the non-polar portion. Okay, so in the presence of grease, for example, here is a non-polar, your soap would be attached or attracted to the grease using the tail end or the hydrophobic end of your soap, and what is being exposed to water, okay, is your polar end. So the COO minus, which bears a negative charge, will be bonded to water via the intermolecular force of attraction called hydrogen bonding. Okay, so since this one is hydrophobic, it would want to be far away from water as possible. And here what we get actually is like a spherical one, where you get our micelle. So the micelle portion is that the hydrophobic end will be situated away from the surface, away from the water, and it is being attracted to the grease or to the dirt. And what is being exposed in the micelle is the polar end, which would have an intermolecular force of attraction to water. So this is how the cleansing action of the soap would be. Now again, the hydrophobic is part of the soap is buried in the micelle, and the polar end will be exposed to water. So again, we term this non-polar portion as the hydrophobic end, meaning water-fearing, and here is the hydrophilic part or the polar portion. So when I'm saying hydrophobic part, this is the non-polar portion, this one here, the tail. And when I'm talking about the hydrophilic part, this is the water-loving. You have the polar portion here, which is exposed to the water. And in water, once you have your soap in the grease, or even your even in the grease, the soap would always assumes a confirmation where it will have form a micelle, where again the hydrophobic is buried and the hydrophilic part or the polar part will be exposed to water. And okay, for other kinds of you call it as surfactants. Now, for other forms of surfactants, with the general term for this soap is actually surfactant. Now, I'm just introducing another term. The surfactant would always have a polar end and hydrophobic end, a polar end and a non-polar end. So in this case, this is not a soap that we are talking about coming from the triglyceride, coming from the reaction of triglyceride, but for other kinds of surfactant, I have to say this often. Other kinds of surfactants. Okay, like this structure here. Like the structure here, you will see this end here to be, you can see an atom that bears a negative charge. No, you have easily the oxygen atom, one of the oxygen atoms that bear the negative part, and this end becomes the polar portion of the polar end. Of course, usually it's bounded to sodium. Once you get a negatively charged oxygen atom, it should be bounded to another positive one. Usually you have your sodium or you can have your potassium here. And you can see on this last part here, you can see that you can only see carbon, 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 carbon. These are an aromatic one. You have carbon, 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 carbon. No? You don't see a polar atom like oxygen, nitrogen, or fluorine here. So here is the hydrophobic part. And if you look at the structure for this and kaning isa, the soap, structure of the soap, you can see that they have somewhat similar structure. The only difference that on the head part, so I have to add here, you have your head. Hindi ako naghimo ano yung PowerPoint. You have your head and you have your tail. And your tail is usually your hydrophobic part. Kani. Okay, so your tail is the non-polar portion or the hydrophobic part. Hydro. The hydrophobic part. And the head, which is the also the polar or the hydrophilic part, the water-loving part. Okay, so you'll see on the structure between this one and the second one, so they have different structure, but more or less, if you scrutinize it, they have the same. This part, they have this part here, which is hydrophilic. There is a polar end here, or they have the polar portion. And there's also this part here, which is the non-polar portion. And also we consider this to be the tail or the hydrophilic part. Okay, so although the hydrophilic part is different, but the overall structure is that there is a polar end and there is a non-polar end with this similar. And you call this one as a surfactant. In fact, this is what you call as the structure of the usual structure of the detergent. Okay. So once in a detergent, another kind of surfactant. When you go to I think you're biology now. If you're doing your biology courses and you're doing the lab, okay. Most of biologists are doing another kind of surfactant. They're using the sodium dodecyl sulfate. It's also another kind of surfactant. And if you look at the structure, you can see, if you scrutinize, there is the part which is polar and there is a part which is non-polar, or there is a part which is the head and there is a part which is the tail. Okay, you consider this one is to be a detergent. So kanang mga kaning detergent, where you can see this one. For the detergent, depending na sa detergent or the manufacturer, you can have from the aromatic ring, you can have then this a number of carbon chains here. You can have the ring here, you can have the ring here, the ring there. Depending if there is a branching here, no. Depending na sa the kind of detergent. And you will see, no, kanang mga body wash, kanang mga, yeah, the detergent, for example, kanang panglaban ninyo, so detergent, you have the, usually this kind, no, nga, you have a ring and you have this one here. But for your, sa yung mga body wash, no, it's a different one. They're not using the sulfate. And you can see, no, but generally you can also see for any kind of detergents and soap and detergent like surfactants, you have the general structure, like again, the polar end and the non-polar end, and the cleansing action will be similar to be like this. And the difference between soaps and detergents are, one, soaps are natural, commonly prepared from fats and oils. For detergents, like the second structure that I've shown earlier, they're usually made from petroleum chemicals. And for soaps, it's prepared from fatty acid, salts, and carboxylic groups. You can see this in the structure, right? You have COO minus, which is your polar end and the tail of your carboxylate group. Okay, but for detergent, you contain the sulfonate groups. And no, sulfonate, this is your sulfonate group. And here, this is your carboxylate, COO minus. And for the soap, the only disadvantage is that although it is natural, it comes from fats and oils, and it's actually good for the skin, no? The only disadvantage is that it will form an insoluble precipitate of salts when dissolved in water rich in metal ions. Sa manang water rich in metal ions, kana mga hard water, no? Mga mo sa mga bukid-bukid, no? Or sa mga isla-isla na there is though the water resource there is usually rich in metal ions. And you will notice pag maligo mo dito magamit mong sabon, magputi-puti na scumbags, no? And it is because of the insoluble precipitate of salt that would react with metals. So, for example, this is the structure of sodium. Kanino, ma-replace na siya with another metal, for example, calcium, magnesium, no, it will already form a precipitate. Magputi-puti siya. Insoluble precipitate. So, I don't know if nakasulay na mo, Ana, but if you are an explorer, no, and live in, or if you've visited places which are very far from processed water, like we have, like we are using in Caron, no? If you are using ka ng mga tabay ng mga water from deep well, and yes, you will observe that you will actually form insoluble precipitates. So maglisod kag ligo kay or di ka kalimpyo kay instead of the dirt that is from your surface of your body, no, you cannot insolubilize, you cannot remove the dirt from your surface because first it will form a salt, precipitate salt, no, puti-puti. And that is one of the reasons why scientists actually find a way to prepare a surfactant that's similar to soap, but would have the advantage or minimizing this formation of insoluble precipitate. And that's the reason why they use the alkyl sulfonic acids, which are more soluble in water. So even if you use, for example, kanang mga kaning mga detergents, even in hard water, kanang mga dito, makalabag yapon o makalimpyo yapon siya. But with soap, no, it's really hard because instead of cleansing, no, it will form insoluble precipitate. Okay, so the challenge is you go to the mga isla-isla. I don't know I haven't been to Siargao. Anyone here is coming from Siargao? Naa ba? Anyone? Isa may nakaadto nag mga isla-isla? Anyone? Uy. Okay na, wala taga-isla dire. Just for kung dili mo taga-isla, if you visited, you know, I've been to Bohol and actually my Bohol. Ang akong lolo di ay, no, sa una. So mga tumig isla and their source of water is kanang tabay nga pud gihapon, no. Lisod gid siya maligo, no, using soap. So the challenge is have you tried using mga body wash and kanang inana, no? Igo, it's better than use soap sa mga inana nga part. Of course, you couldn't use detergent. Murag laing kaayo nga dry food kay yung skin if you use detergent for your body when you're washing, but you'd rather use kanang mga lighter one. This one, the detergents are much harder kanang panglaba as compared to mga body wash, no? So it's like in between the soap and the detergent part. Okay. So I think we'll be wrapping up. Just 30 minutes and we'll finish.
Ma'am, nakita ka ng question, ma'am.
Yes.
Kanang, how about, ma'am, kanang ganing, pag kanang, kasi explanation na ma'am, kanang, magamit kay kag sabon, ma'am, tapos, tubig ulan yung gamiton, slide ay gihapon.
Mas better pa ang tubig ulan, no? Because the tubig ulan, it's actually, usually atong ulan is actually a mixture, no? It contains a lot of carbonates, no? So mas better siya kay kuan siya, more on carbonate siya because of the carbonic acid that would come from the rain. No? If our for example air would contain carbon dioxide and can have a reaction to in water, no? Pag mahimo siyang sa rain, can have your carbonic acid gamay, dili pud daghan. Kasi you have your carbonates. So muna siya, basic ang imong makuan and muna siyang slippery siya. So, di ba mas tsada, no? Mas tsada siya kaysa matukag maligo ka og tabay, right? Kasi nakaligo tabay. I don't know kung nakaabot mo tabay, nakaabot pa kog tabay. Kanang deep well, okay? And it's really hard na maligo nga nagputi-puti ra ng kuan. So, rainwater is much better kay wala siya kay metal ions, no? But the only thing that's rich is na siya a lot of ions that would come from, for example, I have said it, bicarbonates rather, the bicarbonates or kana, no? And it's a basic one, and it would actually make your water slippery. Whenever you have a basic solution, mas slippery siya, no? Mas slippery siya kaysa sa acid. Mana. Okay. So let's proceed. Another reaction of triacylglycerol is the halogenation reaction. Again, so the halogenation reaction would emerge from what you have learned sa organic chemistry, again, in the form of alkenes. No? You'll see in the structure, you can have a lot of functional groups that's present. No? This is your linoleic acid. What are your functional groups? The main functional group, of course, you can see is this one, the carboxylic acid. But in the chain, you can have your double bond. So you have your carboxylic acid and you have your C. And of course, if you remember in your organic chemistry, when you name this one, you will name this after the carboxylic acid, and naming this from alkene is only secondary. So 1, 2, 3, 4, 5, let's say 20, how you name that one, and you end with oic acid, like linoleic acid. So the main functional group is the carboxylic acid, but in the chains of your carboxylic acid, you can see there's a double bond. And in the presence of halogen, room temperature, and some organic acid like acetic acid or methanol, can actually add your halogens into your double bond like this. Now, so this is again one of the reactions of your fatty acids. And if you remember another reactions of your alkene before in organic chemistry, you can also have your bromine. Katobitang red. Bromine is red in color. Pag react siya with your oil or something, and from red, mahimo siyang puti. It means that the bromine, which is brown in color, is consumed to produce your product, your alkyl halide part here. But of course, this one, you still have your carboxylic acid with the halogens here. So kung kanilang siya, you can actually think of this as your alkyl halide, this is your carboxylic acid. So here again is just an application of what you have learned in organic chemistry, which is the halogenation reactions of your alkenes. In the presence of iodine, the iodine will not react to the carboxylic acid, but instead it will react to the double bond in the same way that the hydrogen, H2, would react to the double bond to form this. In the halogenation reaction, the halogen, your I2, Cl2, Br2, no, can react to your double bond in the presence, at room temperature, of course, in the presence of some organic solvents. So some properties of, again, our triglycerides is that it would easily become rancid, or there is this rancidity reaction where you produce the unpleasant odor and taste developed by most natural fats on aging. So if you stock actually kanang mga oils ninyo, dugay na kanyo, wala, butan nyo sa bottle, you'll notice no nga, murag mo vacuum, no? Because there's actually a reaction going on. You can smell, taste, and there's this gas that's actually being developed inside. Again, that will be the auto-oxidation process. I don't know why this slide doesn't show, but you have an auto-oxidation process going on. You can review on that with your organic chemistry course. That kind of reaction where you produce a rancidity odor, no, is the auto-oxidation of your fatty acids, of your double bond, particularly your double bond, your CH situated next to your double bond would go into the auto-oxidation process. Again, the cause of rancidity is the hydrolysis of fat, hydrolytic rancidity. Okay, so you have your fat being hydrolyzed, you have your and then you have your oxidative process, the auto-oxidation process. And the only way to prevent this rancidity is to include antioxidants. Okay, so example of antioxidants, you have your vitamin E, phenols, hydroquinones, tannins. So if you have your food products, let's see if I have here in my slides. If you have in your food products, no, instead of vitamin E, it's very expensive. I'll see if I have. If you have your food products instead of vitamin E, they actually use kanang DHT. Okay, I was looking on my slides, organic chemistry, where I can show you on the auto-oxidation process, just in case makalimot mo. Anyway, ito oras akong isa ka laptop. So again, the process is rancidity, and to prevent the rancidity, no, of our fats and fatty acids, no, or oils, we actually add antioxidants. Again, vitamin E, phenols, hydroquinones, tannins, no. Sa atong mga food products, you will notice ka na mga preserved foods, no? Ang mga preserved foods, some are oily actually. For example, ka mga chili, mga something inan, no? There's a lot of oils and fats there, and kana mga preserved products, no, they actually add antioxidants, and it is for that reason that our preserved food products actually could last long, no? And mga chips, kinaminana, because they would add antioxidants. Para kung na kay fatty acids included, for example, fried siya nga processed food product, no, na yung mga oils na, you don't want it to become rancid if you stored it for a long period of time. So manufacturers would add antioxidants, usually na siya phenols, vitamin E sa phenol, hydroquinones, tannins. No? For some, they would add BHT. I don't know. You should know that, no? You've been through organic chemistry. Kana. And then some plant sources kanang mga, for example, mag-include ka sa imong food product o mga daghan nga mga spices. Now, usually the spices would contain a lot of phenols and would also add to prevent the auto-oxidation or rancidity of your food product. So, manang, if you notice, no, kung mag-store mo, for example, like na mga chili, mga garlic, mga no, it would last long for reasons because kanang mga spices nga magipang add would actually contain some compounds in the forms of phenols, no? Kind of mga derivatives of phenols. Remember your phenol, what is your phenol? You have your benzene ring with an OH. And so some form of that, whenever you see in that structure, then you would know that it can prevent the auto-oxidation process. You know, I remember the slide. Oh, for example, kanang inyong mga ethers, kanang inyong mga chili, no? Na siya yung mga capsaicin and all. So, dili kanina slide. Okay, di ko ka-remember ang sa slide I'm trying to download. Something that I could show you, no? Anyway, so that's it. Just know that once you're eating mga food processed products, there's a lot of fats in there involved. Kaya yung mga chips, no? There's a lot of fats involved there, but manufacturers would always add antioxidants there. Can have even yung mga personal care products ninyo, no? There's also a lot of fatty acids there, oils there, no? Part of the mixture would be some milligrams of oils, and to prevent again oxidation, you have to add vitamin E, no? Para aside sa inyong skin, they would want our skin to have vitamin E to prevent oxidation, no? Especially kina mga oily skin, no? You want to prevent the oxidation kina mga oils in your faces, no? Of course, you have to add antioxidants for if you're exposed to the sun, then instead of your skin, no, it would be on the auto-oxidation process, radical formation would be prevented with the use of vitamin E. So that is for personal care products. And nowadays, again, I have mentioned it's not vitamin E that they use for food processed, but instead they use kanang mga BHT. It's much cheaper, BHT, or mga phenols, other forms of phenols, and particularly from other plant sources. Okay, so that's the reason why they last long. So hanako, so here I'm showing the structures of complex lipids. We have mentioned only the simple ones, the triglyceride, no, where you get your fatty acid bonded to your triglyceride. Of course, once you eliminate your fatty acids, can actually get your glycerol part. But there is a complex one. You have the phospholipids, and you also have the glycolipids. Okay, so for the glycolipids, you have the sphingosine, which contains your glucose or galactose, and you have your fatty acids. And for the complex one, there is two types. You have your phospholipids, you have your glycolipids. And for your phospholipids, you actually have your glycerol phospholipids, where you have your glycerol and you have your fatty acids in the structure. Instead of all fatty acids, you actually get your phosphate group. And then some alcohol here. So you call this one as glycerol phospholipids. And then you have your sphingolipids, another kind of lipid, where you have your sphingosine. There's a structure for sphingosine, and get your fatty acid with another phosphate group and a choline. Okay, so what we have discussed so far is just a simple one, but know that there are existing complex fatty acids. Okay, so there is this role of lipids, the structure of membranes, and you can see here that you have your glycoproteins, no? It's actually a carbohydrate with a protein part. You have your glycolipid in the part. So your glycolipid, you have here, you have this sphingosine, and if we look at the structure, I don't know why they included it first here. Just know that in the membrane, no, so if you remember your first topic of biochemistry is the cell structure, and you have in the cell, you have actually in animal cell, you have the cell membrane. So like us, now in our cells, you actually have the cell membrane. In our membrane, the cells, there's actually this carbohydrates, which we call as the glycoproteins, and we have this one, the glycolipids, this part here. that is that mostly comprise our cell membrane. So what are glycerophospholipids? Okay, sure, I should have used my slides. Anyway, so one type of complex lipids is glycerophospholipids. So asa na siya nabilong? Glycerophospholipids. So na siya na nabilong sa phospholipids. Okay. So one is that you have your glycerol again, which would be the structure, and then you have your fatty acid and a phosphate and an alcohol. So look at here on the structure. Okay, you have your this structure here is H2O, H2 here. You notice these two parts here is similar to what we see with our triglycerides or triglycerol, where you have your esterified fatty acid, cetyl bond O, and then you have your H2, 16, 17, 18. No? So this is 18 ring. That's actually your stearic acid bonded to your glycerol here. And you have here, for example, another kind of fatty acid, but one of the carbons from your glycerol is bonded to phosphoric diester here, or phosphate group here, PO4. Okay, and you can see here that from here, nashay another component. We call this one as choline from the phosphate group or phosphoric diester. So anong diester na siya? Phosphorus oxygen is bonded to carbon and phosphorus oxygen is bonded to carbon. So more siya ester. P double bond OO, phosphoric ester. Diba kanina C double bond OO, this is an ester. This is a common ester. But if you have carbon replaced with phosphorus, so this is a phosphoric diester. P double bond O, P double bond OO here. Okay, so this part is a phosphoric diester. And from the phosphate group, there is a group of molecules called choline that's bonded to your phosphate. So what is choline? Choline is like this. Now you have, it's like an it's like an amino acid rather. Now you have your N, CH3, CH3, well, it's not chiral, bonded to N plus CH3. So look at CH3 and then CH2, CH2. You have here choline. And this part here this structure here is what we call actually as lecithin. And this lecithin, this particular structure having your stearic, linoleic, and this one is a lecithin. And the name is familiar, right? You can see that in a lot of your kind of multivitamins. Okay, so this is another glycerophospholipid, a part of a lipid structure. Okay, so the general structure again is that you have your glycerol here, where you have your fatty acid, cetyl bond O, R, cetyl bond R, so your R can be different. And then you have your phosphate group, and you have your another R group here. So in this case, if you have ethanol amine, you have 1, 2, doha ethanol, and you have your amine, and then an OH here is supposedly an OH. That's why you call this one as ethanol, 1, 2 OH, and amine, ethanol amine. And this kind of glycerophospholipid, na gitawag siya glycerophospholipid because you have your glycerol here, and you have your phosphate group, and this one is a lipid, so glycerophospholipid, same as this one. But in this case, you have your glycerophospholipid also. This one is a choline group, and you have your phospho. So glycerol, phospho, this one is already a lipid once you have your glycerol part here. Okay, so the earlier example, once you have your choline, we call this one a lecithin. And if the group bonded to your phosphate is ethanolamine, you call this one a cephalene or phosphatidyl ethanolamine. The common name is cephalene. So you have your R group here, Pendisa R, no, comes from your fatty acids, but you have your ethanolamine, you have your cephalene here. And your cephalene can be depending on unsa siya nga R group bonded to your phosphate. So again, this kind is a cephalene. You can also change this one to your serine, an amino acid bonded here. So you notice this one are found in formula for your baby products, no? Usually sa mga kanila, sa mga gatas. And of course, you have already mentioned what's the importance of this. So you have another glycerol phospholipids. Now you noticed here you have your CH2O, CH2R, and then you have your phosphate. You have your bonded a group here bonded to your phosphate group. And in this case, you have looks like a sugar, no? In fact, this is an inositol. This is like a sugar. So depending on this bonded here, you can call this one as phosphatidyl inositol. This is an inositol actually. So you have your ring here. It's like a sugar monosaccharide, but the hydroxylated hydroxylated one, you don't have an O. Instead, you have a carbon and OH here. So this is again phosphatidyl inositol. And here you can see in the structure is PIP2 or phosphatidyl inositol 4,5-biphosphate. You can see in the structure from here, no, this is more phosphorylated more. You see a lot of phosphoryl group here, PO. And you can see here in the structure, you can see in the structure here, you have your CH2, CH, and O, and you have here the glycerol, right? You have your CH2, CH2O, you have 3 carbon here, and it should be an O, but one of the carbon is bonded to phosphate group, like this one. But for the phosphate group, one of the carbon 1 to carbon 5, so 1, 2, 3, 4, 5, 4 and 5 rather, 4 and 5 is substituted with phosphoryl group here. And kani siya, derivative rin siya. But you'll notice on the structure, this is still a glycerophospholipids, only that on this structure here, the OH is replaced more with the phosphoryl group. So another kind of lipids, a complex form, if you notice on the general, you can see here is the sphingolipids. It's a nice sphingolipids. The single lipids we have here is still a phospholipids. When you say phospholipids, in the structure is you can see a phosphate group. Okay, the glycerophospholipids, you can see the glycerol structure. In the sphingolipids, you can still see the phosphorus group, phosphate group, but it is bounded to the sphingosine, and you can see some fatty acids there. So on some is sphingosine. So we'll look at on the structure of the sphingosine.